everybody. So I found that I really don't want to go on the third day of this thing because I've sat through 2 days of things that I should have talked about in this presentation and didn't. And then last night I had a really scary comment come up that, you know, if you looked at that partner slide, AMD is right in the middle of it, and I'm the only person actually talking about AMD. So I was wondering if I might need body armor to get through this. So to meet that, what we're going to talk about today, and I made this topic rather than any kind of a table of contents because I jump around a lot. Some background, what this new processor is that we are working on, which is the Zen core processor, and what our approach is to bringing it into coreboot support and where we are today. So some background. AMD actually has a very long history with coreboot, going all the way back to their Geode LX processor. But it's been an on and off again relationship, as a lot of you can testify. And when they're off, they are really off. They are absolutely absent from the community. But we've been working with them for a couple years now to try and bring them back into the community, and they seem to be going well with that. One of the things that's come up is, I don't know if you've ever heard of their reference code, it's called the GISA, AMD's Generic Encapsulated Software Architecture. There's a test later. And all of the coreboot support except for the GLX is based on something called Architecture 2008 or version 5. This new processor is actually based on version 9, which came out with the Zen cores, and that's presented some challenges for us. But they actually had even some open source versions of AGISA version 5 back in the 2011-2012 timeframe for a couple of generations of processor. So if you want to go back and look at some of those things, they're actually out there. You can see what the source code looks like. But they are actually in a binary kind of mode like Intel is today. So the new AMD processor that we're working on, it's called Picasso, for those of you who love those code names. It's called Family 17, great naming. But it is an AGISA version V9 processor. When they went from V5 to V9, don't ask what happened to the ones in between, they made the decision to drop legacy boot support. So it was designed to be optimized with UEFI and UEFI alone, which means all of the previous coreboot implementations don't work. We had to start from scratch. When they optimized it for that, they made a lot of assumptions about Tiano Core being involved in their firmware. So we had to come up with a way to accommodate the dependencies on infrastructure that is built into Tiano Core and obviously available to anybody doing a UEFI BIOS, but not readily available to those of us in the coreboot world. So we made a decision which isn't popular with a lot of people. We decided to leverage the Intel FSP, which was essentially a way for Intel to get their reference code, which was UEFI dependent, into coreboot. And so rather than inventing yet another set of interfaces for coreboot, we decided to try and use that one. So there was standard existing software already written in coreboot and in Tiano Core to do this sort of thing. It was intended for this purpose. And again, it avoided creating yet another interface. So that was the approach we took. And in doing so, this carries with it a lot of assumptions. And one of the assumptions is this boot flow, which is sort of Intel-centric, but works for most x86s. Thanks, Ron, for letting me steal this. I actually got this from Ron's presentation yesterday. That's right. So it's super odd I actually did this slide, right? That I cut this out of. But any of it that's worked with coreboot understands these are the stages you're going to normally go through. You do the boot block, and then you do a ROM stage and train memory, and then you get rid of your memory training stuff and go into the RAM stage and get set up to go find your operating system. And we thought this was okay. It's an x86, right? Except AMD decided to do some interesting stuff for us. So there's actually a security core, and you can, those of you who are Intel centric can think of this as sort of like the ME. The platform security processor actually trains memory for us. So when the x86 cores come out of reset, DRAM is done. It's sitting there waiting, and the PSP has kindly copied our ROM image up out of the SPI ROM into DRAM for us. We don't even have to go do execution in place. It's just there. And the hardware doesn't actually have the capability to do cache as RAM. It can't do it. You have to use the PSP core to train memory, which sort of changes that flow, because when the x86 comes out of reset, we're here. But all this red stuff didn't get done, which left us with a bit of a mess. So we had to start figuring out how to accommodate this. And at the same time, we were trying to figure out some other issues. So some of the implications of that are you don't need FSPT, but that's not that unusual because there's a lot of Intel processors where you can run open code to set up temp RAM. We don't really need FSP-M because memory is trained for us, but there's a lot of things that we didn't do at the end of memory training. So we still use it for that, but we don't actually use it for training. We still use the FSP-S. Coreboot implications, we don't need boot block and ROM stage because RAM stage is, we can run out of DRAM. But there's a lot of important things that happen in those stages that haven't been done yet. And some examples of things like that are as you go through and get ready to launch your RAM stage, coreboot wants to do things like tear down cache's RAM. And it wants to copy all the stuff that's in cache's RAM into CBMEM. Well, there is no cache's RAM to tear down, and there's nothing to copy. So we ended up sort of pushing these three stages together into something we called the hybrid ROM stage. So we actually run boot block as an ELF so that we can accomplish this mode switch and the jump and some other weird things. There's not a whole lot in boot block, but there's stuff that you have to do. And after listening this morning to what we want to do with vboot, this model doesn't work a lot, but so we still have to set up FSPM, do the UPDs, and call FSPM and set up our CBMEM. We still do that. And we still have to set up our MTRRs, which we do over here, but we're doing this in a very shortened path to get there. And then we get into our RAM stage, which really is unchanged, other than the fact that the PSP actually found it for us and copied it. Some other interesting things, if you're really x86 centric, normally you consider the reset vector, FFF0, actually maps into SPI-ROM. In this case, it actually maps into DRAM. So all of this runs out of DRAM, even though it doesn't look like it does. So we've been working through a lot of this stuff. So we have tried to maximize our use of the existing FSP. So we still use FSP-M as a naming technology. It still has the same entry points, but we don't necessarily do the same things that Intel does in that particular call. We created that hybrid ROM stage. And what we did to satisfy the dependencies on the hybrid ROM stage is we actually reserve a little piece of memory, and we build what looks like cache as RAM, and then we let coreboot tear it apart for us, and then we throw it away. This has not proved to be a popular solution. So we're currently rethinking that. We're actually reworking that right now. So where are we? These talks go really fast. We do have a preliminary version running on an AMD reference design. This is not a design that you can go out and buy. There's a handful of them in the world. But it will work. It boots Linux. It boots some other things. We expect to have production-worthy versions in 2020, but it's actually showing up in coreboot.org today. So pieces of it have already been in review. Pieces of it have already been merged. So I invite you all to go look at it if you are interested in that. Right now, we're still working through things like ACPI. Based on community feedback, what we're going to be working on in the short term is we will be going to FSP 2.1 so that we're on a little more stable footing with Intel. We'd like to keep that consistent. We're probably going to abandon the hybrid ROM stage approach and just build a whole new stage and environment, which we are creatively naming PSP stage, to accommodate the fact that PSP has gotten DRAM up for us. So we're just going to do all our cleanup stuff in that PSP environment. We don't really like that name. It's very AMD centric, but since this is the only manufacturer who's putting out processors that train their memory this way, I guess they get to have that name until somebody else comes up with a coprocessor trained memory. But it will support AMD Family 17 and beyond, and probably include some of the other current AMD chips that are based on Zen Core. So we're going to eliminate that virtual car structure that I talked about. That may actually have already merged today. I didn't check on the merge queue, but I think it was going to merge today. But we're going to have a very lean RAM stage, and then maybe be able to accommodate Linux boot better that way. So that's our goal, is to get to a point where we can quickly and with as little code as we can run in the x86 get to the point where we can call a payload or potentially switch over to a Linux boot kind of solution. With that, are there any questions?
Oh, we did have microphones over there, so we'll use this one. Sorry. They vanished.
Thanks. I like that you are going to a different approach with the stage now, because I was one of those people where the hybrid ROM stage wasn't very popular with. But I still want to ask, why do you need a separate stage at all? Because with all the other stages in coreboot, we really have a reason why we need to switch to a new execution environment and tear down the old one for some reason or another. And in this case, I don't really see why you can't just put it in the beginning of the RAM stage, because the entry point of the RAM stage doesn't need to be a sacred cow, right? We can have a different entry point for a specific SoC or platform. Why can't you just do that?
So as we looked at this, we tried it, and it was going to require a huge amount of change in the entry point of the RAM stage. And we can talk about that offline. It's not something that we could cover here, and get some of the other guys involved that are a little deeper into that exploration. But it turned out we needed a buffer in there. We needed some kind of a shim to get to the point where we weren't just completely ruining RAM stage.
Okay, yeah, I would be interested in the details, because I haven't heard them yet.
Yeah, we've been pushing some documents up to coreboot.org to try and explain that too. So yeah, let's have a different conversation on that one.
Okay.
Anybody else? No?
Oh, I'm remembering something that I think I can tell this story because all the people who worked at AMD at the time are gone. So I'm remembering a funny story. All the people who worked at AMD at that time are gone, so I can tell the story. This is 6 years ago, and this is when they were going to all be an ARM company, and so they had the 64-bit ARM and a 32-bit ARM, and a 32-bit ARM, did memory training, and so we said, so you're going to open source that, right? So we can see that code. And the immediate response is, nobody ever wants to see RAM setup code. So no, not going to do it. But it was ironic because, of course, we'd always seen RAM setup code from AMD. But are they going to open source the RAM setup code?
So here's the on again, off again relationship. So I've been talking with them since 2011 about open sourcing it. They actually did it twice for 2 different processors. In the past, this conversation has been going to executive management at AMD and dragging them kicking and screaming to the chasm of open source and coreboot, where they immediately, when you turn loose of them, run away. The current generation of executive management at AMD actually, of their own volition, walked up to the chasm and went, it's not that deep. So maybe. And it's much better than we've had in the past. So we're pushing for it. Nobody at AMD is saying no. Everybody's saying it would be hard, and that's progress. Anybody else? All right, well, thank you very much.
Thank you.